So there's other definitions of acids and bases. This is the Brønsted-Lowry definition of acid and base. They didn't actually work together. They just happened to come up with the same idea at the same time, so they both get credit here. But in the Brønsted-Lowry definition, an acid is a substance that donates an H+. And so here we have an acid down here, and when it gets added to water, that H+ bonds to the water and forms what we call the hydronium ion. Here you can see a specific example of that. We have hydrochloric acid, so it has a hydrogen there, and so it is donating that hydrogen. When it dissolves, it gets rid of it. It pops off and it goes somewhere else, and in this case it's going to the water there, and so then that's what forms our hydronium ion here and the chloride ion. And so you'll notice we still have that H+ being involved here, like in a Arrhenius definition, but the Arrhenius definition can't catch all cases, and so there's exceptions to all of these definitions. There's exceptions to this one, but this catches some of those exceptions. And so then we have a hydronium ion here, which is what gives us an acid solution. We're going to go into an example of a base now as well. So bases, as we've mentioned already, are acceptors. And so in this particular case, water is going to act as an acid, and it is going to donate a hydrogen. It's going to get rid of that hydrogen, give it to the base, and the base has accepted that. And so the water is donating and acting as an acid. The base here is an acceptor, and so we end up with the ammonium ion and the hydroxide ion. Notice we have that hydroxide there again. But the ammonium didn't have a hydroxide to give up the way that the Arrhenius definition defines it, but we still end up with hydroxides in water, giving us a basic solution. So on this one, we are asked to identify the Brønsted-Lowry acids and bases, and so if this one here, I'm going to show you the way that I cheat, and I will point out that there's a hydrogen here bonded to a polyatomic ion there, and I recognize this as nitric acid. Because of that, I know this is an acid, and so it's our Brønsted-Lowry acid, which means this one here must be the base. For the next one, I'll show you how to actually identify the acid and base here. And then we end up with an acidic solution. On this one here, I'll show you the Brønsted-Lowry way of doing it. And so looking at the two sides, it looks like this compound here has lost the H, so it is our hydrogen donor. And since it's our hydrogen donor, that makes it the acid. Over here you can see that this one has gained a hydrogen, and so the water gained a hydrogen, so it is the hydrogen acceptor. And because of that, that means it is the Brønsted-Lowry base. And again, we have an acidic solution because of the presence of the H3O there. In any acid-base reaction like that, when we have the pairs, it forms the other piece on the other side is called its conjugate. And so an acid has a conjugate base, and a base has a conjugate acid. You can use the charges to help you identify them usually. And these reactions, because they are weak bases, as we'll get into, or weak acids and weak bases, as we'll get into in a bit, are reversible reactions usually. And so then the reverse process, we would switch or swap the names, but you have an acid base conjugate pair, and here we have the base acid conjugate pair, and there's always two conjugate pairs within this. Technically speaking, the way it goes is you have a acid-base pair for the forward reaction, and then you have an acid-base pair for the reverse reaction. But there's always two pairs there. So this is actually the HF that we used on the last example, and so we've already identified this as the acid, and therefore the water was the base. As I said, we looked over here to see what was formed from those, and so since the hydrogen lost the, since the hydrogen fluoride, the hydrofluoric acid lost the hydrogen, then the thing over here that it formed, the fluoride ion, is its conjugate base, and you can see that label there. Whereas this one here, it gained the hydrogen. We went from H2O to H3O with the charge there, and so then that makes it the conjugate acid. Of course, in the reverse reaction, the backwards reaction here, these arrows would go in the opposite direction, and you can see we switch what is a gain and loss for each of them, and you still have these things doing that. So if I just point out this one here, for example, it's our conjugate acid. So now in the reverse reaction, it is the one that is losing the hydrogen in the reverse. And so to form it, it gained it, making this a base and that the acid, and the reverse process that's lost it. So this is still the acid and this is still the base. This here was the other example that we did, and so this was the ammonium and ammonia and ammonium, and so these two here being similar is our acid-base conjugate pair, and these two here being similar are our acid-base conjugate pair. This doesn't get into it here specifically, but this one here would be the base, the acid, the base. So for these here, we're going to work these out, and we're going to do the conjugate acid conjugate base on the first half here. So keep in mind, for these to become the conjugate bases, they have to donate a hydrogen. And so we're simply going to be writing out what's left over after we get rid of the hydrogen. Don't forget the charges. So hydrogen has a 1+ charge, and so these are simply going to have you're going to subtract out that 1+, which means all of these are going to end up at a 1- charge in these cases. So the H2S is going to form HS minus, and the H2CO3 is going to form HCO3 minus. Here we're coming up with the conjugate acid, so these are going to be accepting the H+. So we just have to add an H+ there, and because of that, these things are going to have +1 to their charges. And so here it will be HNO2. Usually the H is written at the beginning, and unless there's other H's there already, which is what happens in the next two. Here, when we add an H, we're going to end up with 4 H's instead, and then a positive charge. And here we're going to add an H, and you'll notice we end up with OH2, but you should recognize that as water. It is normally written as H2O. I will be honest, when it comes to balance equations, and we'll get to that later on, I find it convenient to think of water as HOH, as a acid, the hydrogen ion bonded to a base, the hydroxide ion. It just makes balancing a little bit easier, and I'll point that out when we get there. I will also point out that, as I said up here, these all ended up with the same charge. That was simply because these were all neutral. You'll notice we had things that were neutral to begin with and things that weren't, and so not all of these ended up with a charge. Some of these can have different charges or be neutral after forming, or as the acid forms the conjugate. It just depends on what the acid originally was. So here we're asked to identify whether they are a acid-base conjugate pair, and so it's a matter of whether they are one hydrogen off from one another. So yes, here no, because there's a gain or loss of 2 hydrogens. Here is a no, because there's those oxygens that come in randomly from this one. Here it's a yes, because they only differ by 1 hydrogen, and here it's a yes, because they only differ from 1 hydrogen. And we've seen these two already in examples at least. So here again, we're going to identify the acid-base conjugate pair, and again, I'm going to use my pen here, and we have this is the acid. I'm using the Arrhenius definition for that, and so over here it forms our conjugate base, which means our other pair has to be a base and the conjugate acid.